My name is Heston Bryant. I'm on the thermal analysis team as part of the flight analysis division of NASA's Launch Services program here at Kennedy Space Center. We're hosting thermal fluid analysis workshop virtually this year, and we have Darren and Florian of Siemens to present some software and some simulations that they've put together for us here. And looks pretty in-depth demonstration on the way as well. So I think we'll go ahead and get started, and we'll hand it over to you guys.
Awesome, great, thank you. I really appreciate that. So today, Florian and I are going to kind of start out with a little explanation on a co-simulation we did with SimCenter 3D, AimSim, which is our system simulation tool, and how you can kind of integrate and co-simulate them together for thermal space systems design. And we have a specific use case that we provide different workflows through and how we designed and develop it, which Florian will explain in the latter part of the presentation. And then after this, we have a couple more demonstrations or explanations on space systems design using AimSim. So feel free to stay when this presentation is over. We have about a 60 to 90 minute session today. Okay, so as we know, kind of when you're designing these satellite propulsions or any level of a thermal management system in space, one of the biggest threats is really the stability of thermal analysis and how the equipment's going to operate in that mission profile or during the mission of its orbit, right? And the thermal management system should be able to or needs to be able to not only regulate to a specific temperature, but to be able to cool down equipment to make sure that it doesn't overheat, cause any degradation, or have any level of a phase change that might cause any issue later on with the mission of the propulsion system or of the satellite itself or rocket design. Now, when we look at this two-phase mechanically pumped fluid loop, we really are trying to achieve that phase change, right? We know that there's going to be a phase change, so we want to really be able to keep that temperature stable during that phase change, but also allow the pump to have some level of control on what flow and how much heat is dissipation, right? So as we know, there's the conductive heat, the radiative heat that you have variable throughout this system as well. And if you see on the right-hand side, right, we kind of have that thermal control loop where we have the evaporator, the condenser, a pump, and we have different kind of heat that's brought in from maybe different electronics. Maybe we have some different platforms of instruments. Maybe we have some other electronics that's causing it, but we want minimal temperature change. And on the left-hand side, we kind of have that circulation of heat dissipation, right? So we know that you have your propulsion tanks and you want to have maybe some reclaimed waste heat, but you want to be able to push fluid or push fuel through that level of radiation to regulate how that heat exchange or even how the temperature is going to be regulated. So when we think of designing a thermal management in AimSim, the right-hand side is what we call a V-cycle, and it's really the concept of you're developing a model or developing some level of prototype, and you start maybe from a concept phase or a high-level system model phase, and that's really where AimSim hits the sweet spot. So AimSim is a multi-physics, multi-domain simulation tool that allows you to drag and drop different components and have the math embedded underneath them, right? So if we look at what we are truly trying to analyze in that fluid loop, we want to look at where's the power dissipation. Are we able to maintain the temperature based on the controller logic, based on the sizing of our different pumps or of our different fluid network, and what fluids are available that we can use, and can we try different fluids in that network to get the best stabilization of our temperature dissipation or temperature control. So when we did this design of the model, we have just an overall behavioral and looking at the dynamics of, okay, what's the impact of the heat load coming from the system or on the system itself, right? What's the power dissipation based on how much demand is inside of that pump, right? And are we able to maintain the temperature throughout that process and for how long? And on the right-hand side is the actual AimSim model. So if you look, we have different fluid definitions, right? So we're using a specific refrigerant. We have different material properties that are defined that we looked at for that heat exchange. And Florian will go over this in a lot more detail on how not only the model was set up, but how it was discretized and set up to be able to co-simulate with what we had from a 3D standpoint to get the best fidelity out of the model. We have different signals that we send in that are different heat fluxes, and we get temperature readings out of them But ultimately, we're looking at a pump that is sending a refrigerant and seeing that heat exchange and dissipation across it. In that model, we have a pump. On the bottom, we have an accumulator, and we have different sections of the pipe that we can get different sensor readings off of it that ultimately you can use when you do this level of co-simulation within the tool sets. Why would we use co-simulation? What is the main benefit here, right? And the true great thing with AIMSIM and a lot of the Siemens technologies is we have seamless data transfer. So we have the capability to co-simulate with a multitude of platforms, not only in the Siemens platform of SimCenter, but also externally to third-party tool sets through FMI. But the main challenge was we know that there's some disjoining, right? Or maybe some siloing that's happening. And it happens quite often when you have any level of design that might be between the 3D level of an analyst versus that system simulation analyst, and how are they going to work together? How do we pass off different data, different parameters of our CAD? And the main solution was, we said, hey, why don't you take this 3D thermal multiphysics solution and have it link or co-simulate with AIMSIM in a real-time level environment, right? In that SimCenter 3D multiphysics, we can look at the condenser, we can look at the evaporator from a 3D structural standpoint, and then integrate it to AIMSIM, right? And as I mentioned before, with AIMSIM, there's different levels of fidelity, different ways of modeling. So if you see there's kind of these boxes that are part of that subsystem that you saw on the previous slide, where we have the pump, right? And we maybe have different commands or controller logic going into that pump. We discretize the evaporator over 5 different sections, as well as the condenser. And then we have the tank or the accumulator tank that really models that different transient solution that you would have, but then have the ability to have that transit simulation with the phase change co-simulated with what you have on a 3D standpoint. So really allowing this level of taking the strength of both solvers, the fast use of what a system simulation product would give you, but then also leverage what SimCenter 3D would also offer from a multi-physics standpoint. And then now Florian's going to explain how he fully set up the model, developed the different boundary conditions, and set up the geometries within the SimCenter 3D.
Yeah, thank you, Darren. So yes, so before jumping into the co-simulation setup, just a few words about the boundary conditions, because we are going to present some results, so it will ease you the understanding of what we will present so far. So on the AMSIM side, as Darren mentioned, we use the R123 working fluid and define the flow rate for the pump and also the high and low pressure level for it. So that's basically on the SimCenter AMSIM side. If you have like questions on more details, we have a backup slide for the remaining boundary condition on that model. Then on the 3D side, so in thermal multiphysics, so we had to model completely the condenser and evaporator geometry. So for that, we used a reference paper where we derived the geometry from it, and we decided to use a 5 legs condenser and evaporator geometry for it. So then what we had to define and what matters really for the heat transfer is like the thermal resistance between the pipes and the plate for both the condenser and the evaporator. So we had to define that. Then we followed basically the boundary condition of the paper to have a baseline to which we can compare the results we were obtaining. So we defined temperature constraints on the condenser pipes of -25°C. And then to model the dissipation from the equipment, we applied the 600 watts heat loads on the evaporator plate. Then just specific words for co-simulation. So for doing co-simulation in SimCenter 3D thermal multiphysics, we use what we call thermal convective zones load, which is a specific boundary condition in SimCenter 3D. And we use those boundary condition as a co-simulation interface. And with those interfaces, we model each serpentine leg. So if you remember the previous model that Darren presented, each leg is basically one block in SimCenter AMSIM. So that's how we define the boundary conditions. You can go next, please, Darren. So then the co-simulation setup can start. So the first step for the AMSIM user is to create the user COSIM interface block. So several interface blocks are available to the SimCenter AmSim users, and the one for co-simulating with SimCenter 3D thermal multiphysics is the user COSIM. So then, since you have the interface blocked, you have to connect all the signal converters to the interface block. So basically, it's you connect each block to the thermal convective zone on the 3D side, as I mentioned before. And for this use case, what we decided to do is we decided to extract the heat flow rate from the AmSim model, so basically from the 3D simulation, and send back the solid temperature that we will compute on the 3D side. And we did that for each leg of the serpentine. And the last step is to generate the AmSim DLL file. So this file is used by SimCenter 3D to communicate. So it's really our open door, and I would say our communication way, to communicate between the solvers. So once you have generated this file, you can proceed with the SimCenter 3D model setup for co-simulation. So next slide, please, Darren. So on this slide, yes, I created a short demo just to show you the 3 steps. It will be more like meaningful, so you can start the video, Darren. So yeah, so the first step is to activate the solve co-simulation toggle and to create a modeling object of type of external solver. So this modeling object will specify the DLL that you have generated in SimCenter AmSim. So once you have selected this DLL file and added it to the solution, you will be able to connect and basically discuss with or talk with the SimCenter AmSim. So then we start the co-simulation command. So it's a dedicated user interface where we can read the external solver, so here AmSim. And as you can see on the right side, when I select the solid temperature, which is an output for my SimCenter 3D model, I can only select the output, and respectively the same for the heat flow rate, which is an input. So using the DLL, we can see directly all the available variables from the AmSim model, and then we can just drag and drop or add them and connect it to the thermal convective zone. So the whole process here, it's accelerated, but it took only 2 minutes to connect both solvers. So you click on the slide. We'll go to the next. So then once you have set it up this, we launch the solve. So what is interesting during the solve is that we can track results from for both solvers from the SimCenter 3D user interface. So you can start the video. Yeah, thank you. So during the solve, in SimCenter 3D, you will have access to 3 log files, one for multiphysics, which is our platform to exchange information, SimCenter 3D thermal flow, which is the thermal solver, and the external solver, which is the AmSim solver plugin. So the first step is really the start of the solve. And then you will see we will start to write like all the time steps from the AmSim model, and we can track all the variables we are exchanging between the model. So you can see really in real time how all the variables evolve, and you can track the convergence during the transient simulation. So here Q5 evap is like the last block of the evaporator that where we extract the heat flow rate. And we can see exactly the same for the temperature. On the right side, you have the log file that the AmSim DLL writes. So this is really interesting for like the SimCenter 3D user to also visualize what is happening on the SimCenter AmSim side. So that's like the real-time communication during the analysis. Next slide, please, Darren. Yeah. So then before going into the results and what is really interesting with co-simulation, we just did a short comparison between a model that is that involves only the SimCenter AmSim part and the model I just presented with co-simulation. So as you can see here, we have the same heat imbalance, so which validate basically the connection and communication between two models. But when we look at the temperature profiles, you can see that we got some differences. So this is mainly due because of the 3D geometry that modifies the response time. So adding the 3D part of the heat transfer allows the solver to capture more the temperature gradients. So basically now we have the 3D effects of the heat conduction on the 3D side, which we cannot really have with SimCenter and Sim because it's like a 1D 3D, 0D 1D solver that does not allow to capture the 3D aspect of the heat transfer. Also here, I would like to mention something that is really specific to co-simulation is like the time step effect. So as you may know, when using system simulation software, time steps can be really small, but as the solver is really fast, the computational time is not really high. But when we connect to a 3D software, like the timestamp matters because we can use small time step, but then we will increase the computational time. So here we use a constant time step just for the sake of this this demonstration. But as you can see, the timestamp was quite large, so this is why you can see this small, like I would say, like upside down on the transient profile. But then at the end, we reach the same results. Next slide, please, Darren. So about the results, what is like what are really the benefits for a SimCenter and Sim user is that now we can access the 3D dimensional nature of heat transfer thanks to the SimCenter 3D thermal solver, and also thanks to that and the 5 connections we define on the SimCenter MC model, we got also an unequal heat flow rate distribution that we couldn't achieve without the 3D computation of the heat transfer. So now, thanks to that, co-simulation can really support system engineer while designing a loop heat pipe because they can get more like details and information from the 3D solver. Next slide, Darren, please. Yeah, so as perspectives and next steps, that those are like solutions that we are currently investigating. So we can investigate new condenser design, so something more complex on the 3D side, I would say, without modifying a lot the SimCenter MC model, which is really interesting for a system engineer. So for example, we can investigate a fully immersed condenser to use both sides of the condenser plate to extract the heat to the environment. And another thing that is more like to get closer to the use case that Darren introduced in the first slide is to consider multiple equipment configuration. So to really leverage the 3D aspect of SimCenter 3D by investigating the heat loads repartition on the evaporator. Because as I said, the 3D computation can take into consideration all the local dissipation of the equipment. And using that, the system engineer can focus more on the design of the low heat pipe rather than on the modeling assumptions and how to have a meaningful 1D model. So I think that's all for that. I saw a question from the audience.
Yes. Yeah, there was one question. It was, can this type of co-simulation be done by SimCenter 3D and Flowmaster? And if so, what would be the main difference?
Okay, so it's a good question. We are currently collaborating also with the Flowmaster software. So it's in our roadmap on the SimCenter 3D side. So yeah, yes, it will be possible. And the idea is we develop our co-simulation interface on the SimCenter 3D side to be as generic as possible to have basically the same user workflow whatever is you are using SimCenter and Sim or SimCenter Flowmaster. So you won't see big difference.
There's another question that just came in, and it seems to be more interested. The question's more interested in computational costs with this sort of co-simulation.
Okay, I'm reading the question.
Oh, okay.
Okay. So yeah, so for example, for the model I presented, first I'm gonna give some numbers about the computational time. So the SimCenter MC model is really fast. It's like the order of magnitude of 1 minute, I would say. When we defined the co-simulation model, it took 30-ish minutes. So, and it's basically due by like the communication between the solver also, but mainly because of the 3D simulation. So then, yes, as mentioned, I think the user needs to evaluate what would be, I would say, the benefits from the 3D side, and because there is a cost associated to, for example, every 3D simulation is more expensive than 1D. So of course, when you connect to 3D as a system engineer, you have to expect some computational costs. So it's like a compromise to find. So currently, to reduce that, we're investigating. I can say that better like time step methods to really give the user the possibility of speed up the, for example, the run in some part of the transient profile, for example. So, but yes, it's there is a cost associated to that, of course.
All right. I don't see any more questions. Thank you for those answers. Very great.
Welcome.
Awesome, great. If we don't have any more questions, thank you for joining for this portion of the presentation. Florian, I thank you again for setting up the analysis and being able to go through a further in-depth detail for any questions that the audience had, but also show how we were able to really leverage SimCenter 3D with co-simulation with AIMSIM.
Yes, thank you for showing this. This is very useful to be able to kind of centralize where you want your computational power and to break apart these systems like that. I'm sure the use cases are endless for systems where the physics are really important at one point, like the exchanger, and then can be a little more broad or 1D elsewhere. This is great use. Excellent. So now this is continuing. We have the same presenters here going into rocket propulsion system simulation. Now this is a different. This is not so much about the co-solver, correct?
Yeah. So this is more of doing kind of trade-off studies, or really looking at different ways you can look at propulsion systems or trade-off studies using system simulation. So the first one was really just leveraging SimCenter 3D co-simulating with AIMSIM. These next two sections are going to be talking about, first one as a kind of trade-off of rocket engine design, and then the second one is going to be how we went through the step-by-step process of modeling a propellant system for an older design of a rocket.
Excellent. Well, I take it away.
Awesome, great. So we went through the process of really and utilized and realizing that things are becoming more and more electrified, right? So we use different references or different analyses that the industry has been analyzing and looking at the difference between maybe an electric fed versus a gas generator rocket design, and using system simulation to really see the trade-off or benefit between the two. So when we really look at the trade-off of the different architectures, right, we're looking at liquid oxygen RP1 rocket engine cycle, and we're looking at that performance, right? So we're comparing, and you see the two different AIMSIM models there. The one on the left-hand side is electric-driven pump-fed, right? So you see the motor in there, the inverter, the battery, with the same architecture of the liquid oxidizer tank, the RP1 tank, the helium pressurization tank, right, and the combustion chamber or nozzle. And the bottom left-hand side is the schematic. And then on the right-hand side, it's basically the exact same model, but rather than being that electric-driven, we're doing a gas-driven, right? So we're replicating in a system simulation standpoint of what a gas generator would be in this propulsion design. So the main characteristics, when we were just looking at the electric design, we said, okay, this is the characteristics that we found from a reference literature on the motor and inverter. Will have a max power of 1,500 kilowatts, specific 20,000 RPMs. All right. We want to have a electromagnetic loss of roughly 1.5% times the actual power. We knew that the power density of the electrical storage was going to be 5.3 kilowatt per kilogram, and the motor had the efficiency of the motor was 95%, and the efficiency of the inverter was 85. We had the leakage known by the pump, right, in the liquid oxygen leakage at 0.5%, and we know that the casing had a specific mass roughly of about 38 kilograms. And then from the battery side, right, we had a specific cellular chemistry. It was a D-cell lithium polymer cell chemical design. It was cooled by that fuel battery mass that we had that we talked about before. And then a specific maximum cooling temperature of an increase of 40 Kelvin. And in order to meet these requirements, we had a 2% of nominal flow that was used to cool down that battery pack. So when we look at kind of the Aimson model, and as you talk about or think about a system level simulation, because it's multi-domain, multi-physics, we have the green here, which is the mechanical, the purple, which is your electrical. So we have kind of the specific constant RPM value going into that motor, and it has an inverter located. So this is a motor inverter example, and then it's connected up, and we have some thermal analysis, some liquid oxygen coolant that's running through some piping that's alongside or basically goes with the motor itself. And then if you look at the battery pack, again, this is another library located in Aimson drag and drop, but then we have kind of that RP1 coolant, which is that orange that's flowing along the casing of the battery. You see here, this is the specification of the specific battery we use, right? So we talked about that battery density or energy density as well as your C rate. The next characteristics when you really look at the design of these two different architectures is we have our pumps and our tanks, right? So from a pumping standpoint, we knew that the power density needed to be, that 20 to 15 kilowatt per kilogram. It needed to have an efficiency between 0.61 and 0.66. And we had to regulate the outlet pressure and inlet pressures. And we had to look at a specific mix ratio, which you do when you look at your propulsion design in general, right? And the pump itself, we had Suter curves that it was based on as parameters. And then we took spherical shaped tanks, right? So we have different geometries, and you'll see that in the next level of the presentation, the process of importing tanks within Aimson. But you can take different CAD geometries and ultimately import them and parameterize your different tank models inside of Aimson. So we did a spherical shape. We knew that it was going to be an aluminum alloy, so we had a specific material property to it. And the helium tank, so the pressurized portion of it, was kept to 27 megapascal atmosphere. Okay, we knew that there was minimal computation of solid mass, and there was some ullage that we had to really keep into account. But the initial fluid quantity was really looked at from these different simulation models, but also looked at through different burning times. So when you burn the fuel between 300 or the 1200 second mark. So the gas generator, right? So as mentioned before, we had that electric driven and then the gas generated. So we knew the different gas generator and turbine level densities and the efficiencies. We knew that there was a specific pressure ratio to it. And again, this is all from literature and references to different white papers in this study level of analysis. But that's what we have, a liquid propulsion library where you're able to model different turbines, different chambers, different combustion chamber capability to have this level of fidelity within modeling this design. And then the next section would be our the pump of the liquid oxygen the fuel, right? So we had a specific thrust that we needed as a requirement. We had a pressure and we had a mix ratio that we needed to keep in mind. And we had different burning times that we had through the process of doing this simulation and modeling of analysis. So the assumptions, right? So when you are using different data points or maybe minimal access to data, you have to make some level of assumptions when you do your design, right? So we did have a reference paper, but we might have had different fluid properties where there were differences in densities for that liquid oxygen or the RP1. So it might have different, that's what led to us having to scale ultimately the tank size volumes to match up with that test data or the literature data. We use an arbitrary thrust of 70 kilonewtons. We knew that there was some unknowns based on, so we used the cooling jacket based on an engine that we did know. And we didn't have any disassociation, so we used the simple combustion submodel. So the way the calculation is done inside of that, that app or embedded system level simulation. We do have some future work that we're going to do from a Siemens standpoint to generate different combustion maps for RP1 in our tool set. But we know that our fluid mass is going to be based on this dynamic simulation. The results aren't static. So the equation that was given in the white paper or the references, we did a dynamic level simulation because that's the leveraging of system simulation, or even AIM-Sim is the level of transient level calculation or design. So we know that there's some default pressure losses or valves or pipes that weren't maybe explained in the paper or modeled, so or modeled in just a different way. But we knew that there was specific requirements. So the requirements had a combustion chamber pressure that we needed to keep in megapascals atmosphere. We had different thrusts that we had to keep, right? That's 68.9. And we had a specific mix ratio of that oxidizer versus the fuel. Okay, so both configurations, you'll see we're able to meet those requirements, but there might be some different in little bit of target. We try to keep that within the less than 2%. So when we do that trade-off study, right, we look at different analyses. The first one we did was analyzing. Oh, sorry. Let me see if I can bring this up here. Okay. So the first one we looked at was the mass breakdown. So we did 300 seconds of burning, right? And we looked at the global mass of the electric configuration initially, and then where that was discretized, right? So from the gas generator standpoint, we saw a global mass and the discretion of the propellant mass between the two. But as you see, the electrical configuration shows an increase in mass due to the battery pack, the motor, the inverter itself, versus the gas generator. So we're looking at that 7.16 times 10 to the 3 kilograms versus that 6.82 kilograms. But that's the first assessment or way you want to analyze or look at kind of the trade-off. The next level of analyzing for a trade-off study is you would pick another parameter, right? So maybe we did a mass breakdown assessment after 1200, right? So we did it after 300, now we did it after 1200, and now it flipped, right? You'll see that that electric configuration shows that it's slightly lighter, roughly like 0.7%, and that's what you see here on the bottom right-hand side to the reference, to the white paper, and that's when the battery is fully discharged, right? So that's why the 1200 second of burning time was there, right? So we're looking at that point, 26.015 versus that 27.0775. Still same discretization of where the masses are located, where the weight is distributed throughout the design. But in the end, the electric configuration has a slightly lighter mass after burn-off. So when we did this analysis, we wanted to use just the idea of hybrid architecture, or how hybrid architecture could have different levels of analysis or fidelity to a conventional architecture, right? We know we just looked at basic mass and power budget balance, which is kind of the trend that was happening not only from the reference paper that we use, but also for the initial design or thought process of doing this trade-off study. Now, will help, if we go to increase the model fidelity, we want to maybe have better parameter sets for defining that electric machine, maybe capture some physical interactions between the machine, or maybe some thermal modeling, further cryogenic feeding pump and lines. Having kind of a better parameterization obviously will increase the fidelity of the model, but also the accuracy of the model to get more trade-off studies versus just that mass and power budget level analysis. We could have also had a level of better controls, right? So we might have the ability to control that required amount of flow differently through knowing the level of control algorithms. But as you see, just from kind of the two different analyses, the one with the best mass reduction or even power budgeting would ultimately be that electric motor and inverter design versus that generator design. And that would be after the 1200 burning time, so the full dissipation of that battery. Are there any questions with, and this was performed by our business development team. So Stefan Muvad, here's his contact information. He's in charge of all the development of the aerospace sim center simulation for AIM-Sim specifically. Anything, even with the next presentation that I'll be performing, he helped with the design and even the analysis of the different propellant stage, the EPS, for an older design of the engine, but that was just due to reference material. But we as Siemens as an organization, or even in the AIM-Sim aspect, really are trying to leverage different trends in the industry, but apply it to more of that system level simulation and trade-off study.
Great, yeah, thank you. This is relevant to the Electron rocket, right? With the battery. It's really cool stuff to see it kind of worked out on paper and why they went with those decisions. Maybe did you do was this directly with that rocket, or it was just kind of like a hypothetical battery powered case?
It was as I know of, it was a hypothetical battery case. I don't know if it was that specific one, but I could definitely follow up and provide further information from Stefan on what it was.
Oh no, just wondering for more curiosity or anything. But that's really cool because I know they did it and it's working, and I'm sure we'll see more to come of that. So it's a great demonstration there.
Awesome.
Thanks. So do you have a live demonstration coming up next?
So it's I guess for me it's kind of a workflow. I was hoping to have it be a live demonstration. It's more of a demonstration on how you would go through the process in setting it up within AIM-Sim. This new design of this EPS was in the latest release. Unfortunately, it was a beta release. So Stefan wasn't able to get it to me for a live demo, but I was able to discretize it fully through the process and how you would define it. So it would be almost as interactive as if it's alive.
Oh, that's great. We'll take that just the same. I'm sure this is really useful for people in prop. So yeah, go ahead. It sounds good.
Awesome. All right. So the last portion, and like I said, we had roughly 60 minutes to an hour. 60 minutes to 90 minutes that we had for these three presentations. So please feel free to ask any questions. But this last one here was how we designed this propellant space design using AIM-Sim, right? So I keep saying AIM-Sim is utilized as this multi-physics, multi-domain, but a lot of times it's really just to collaborate within these different domains, but also as you have different siloed groups, have them work together better, right? So be able to use one tool set and model all of the system, or even parameterize it, or run different design of experiments or studies in that one tool. So this full workflow that you'll see today, right, I did a step-by-step of a model. It's of that Ariane 5 generic third stage. So that's what we call the EPS, or storable propellant stage. So this really propels the payload to the final orbit. So it provides the thrust needed for the orbit. And then from there, we knew that we had only access to reference paper, so we used something that was ultimately released in 2018, but that's the ACES engine, and it's going to be pressure fed from that pressure gas helium, and we have different tanks for fuel as well as oxidizers. So we have MMH as well as nitrogen tetroxide or peroxide as the oxidizer. So I do always have the disclaimer in there, right? Even though we are using references, it is only based on open literature. So as mentioned in the previous one, right, we ideally want to have the best parameters and the best data as input. But when we're doing this level of benchmarking or analysis from just maybe a partial data set, I just always keep that in mind when you look at this level of analysis. So when we developed it, right, we broke it down to having different subsystems, and you do this with any level of system simulation, right? It's kind of that crawl, walk, run approach, where we design a specific subsystem and link them all together and integrate them together kind of ultimately as one. So you'll see me go through that workflow or that initial workflow, which you can kind of elaborate as being on that V cycle through the system design concept as you gain more parameter sets, and maybe even going into that 3D level co-simulation or even getting to the real-time hardware in the loop or software in the loop type capability. So when we look at the subsystems, we have the chamber, the nozzle, right, the regenerative circuit for the heat exchange. We have a fuel pure pressure valve assembly, which is on the left-hand side of that chamber. We have our different propeller tanks and then a pressure regulator. So the first part really that we started was, hey, let's look at the actual engine itself. Let's start with this portion of the design or of the schematic, and how do we develop that? So you go through the workflow, and we had some reference data. So we use different apps or tools that are part of the AIMSIM functionality, and then we designed and again used references to come up with the chamber geometry, come up with the way that it was set up, the design of the nozzle, and then the regenerative circuit and that heat transfer. Okay. So this is what ultimately the first set of AIMSIM models look like, right? So if we look at the model here, it's composed of two different parts. So the left-hand side is really where we have our fluid definitions. So this is where we have our fluid properties, some engine data that we have from literature, the control valve signals that really are going to let the flow through the fuel of the oxidizer, and those are connected to variable orifices, but they're just one way to represent control valves, but we have further fidelity that we have through the development stage. On the right-hand side, we have kind of this sketch of the engine itself, and that's where you're seeing and noticing a similar to that cycle shown in the previous figure that we had, or for a previous picture, right, of the nozzle, the combustion chamber, the heat exchanger, and the fuel side. So the great thing with AIMSIM is we can take the test data, we have embedded apps to import that data, use it as different inputs inside of your AIMSIM model, or we have these drag and drop components that have a different level of fidelity to them. So the first one, right, and this was the data that we imported from the following reference, and I put it on the first slide as well. But we have something called a test data import app. So you can go through and take a table and import it and use it inside of that AIMSIM model, right? So you'll see that the top, that's a super component with 5 different outputs, and it's connected to what we call transmitters and receivers. Those transmitters and receivers can be at multiple locations inside of your model, but it's a way to really develop the capability of signals at different locations, or using the signals maybe as into different valves or different parameter sets or different inputs throughout your model with ease. It also allows us to easily compare what we have from a simulation standpoint to test data. So having the ability to just click open an app, open a .data file or an Excel file or any data table that you have, and easily input into AIMSIM and parameterize it, not only as inputs into other components inside of your system model, but into ways of analyzing and running different benchmarking capability. All right, so after we bring in that test data, the next thing is we have to ultimately design our combustion chamber, right? So this app, right, it's called the Combustion Map Generator tool, it's really there to compute the maps or the combustion maps for the reactants, right? So we have our fuel and we have our oxidizers. And it will generate these different combustion properties onto the left-hand side, which you see as your fluid definitions, right? So the engine model, we put it as a quite simple, but it's composed of this combustion chamber and nozzle with different thermal ports. So when we chose this, right, the propellants are drag and drop available from what we have as the thermal hydraulic library, but we can also leverage what you're seeing here as that mapping tool, and it will give our gas mixtures. So the way that works with an AIM-Sim is you have a definition of, defining the mixture type, the molecular structure on how much 50%, 20% it is of the mixture itself. And you define different numbers to them, and then you can have that mixture go across or based on however many species you need to, or that's how you even do different trade-off studies. So on the right-hand side, right, you're seeing the mixture ratio as well as pressure for those different fluids within the combustion mapping generation process, all right? And based on whatever submodel, so based on the fidelity of the combustion chamber or of the design that you choose, it'll provide different parameters that you need, right? So you have different operating conditions that you set up, right? The minimum, maximum, the step for not only that chamber pressure and mixture ratio, and then it creates these maps that you ultimately use as an input. The next thing is we have this nozzle geometry definition, right? So we define the position, define the different boundary conditions of heat transfer. So, again, this was extracted from literature, but we were easily able to set up the different boundaries for heat transfer surfaces. We can retrieve the value of the surfaces for heat transfer that you see on the bottom there, based on the geometries that we put and the positioning of where we want those surfaces of heat transfer. And we're really just looking at the upper part of the nozzle, the combustion chamber, because those are really touching or part of that regenerative circuit, and having that capability of looking at different boundary conditions or limiting between the upper nozzle and the lower nozzle allows us to really get this full high fidelity capability, but through the specific geometry set, similar to what we did on the SimCenter 3D side, based on whatever the geometry was of that nozzle. And then the last part we have is the regenerative circuit and the heat transfer. I wonder if I can hide this panel, but so we know that there's going to be some heat transfer between the engine, right? That engine, as we just talked about, was the combustion chamber and the nozzle. We have that fluid flow, which we saw on the first demonstration, right? And then we have our environment, right? So the fuel is used to cool down the top part of the nozzle and the combustion chamber. The regenerative circuit has different cooling channels that go along the wall. So that increases the heat exchange area between those hot gases and the fuel. And then the nozzle extension is cooled with what we have as radiative exchange, right? So if you see here, these different components, so these are conduction components, and this is radiative components inside of AIM-Sim. And then the red is all of your controller logic that we could also use in as signals or inputs for maybe heat fluxes or temperature readings from data as well. The regenerative cooling model we just use as a simple representation of a heat exchange that's between the engine, the fuel, and the exterior environment, right, the atmosphere. The cooling jacket we considered has 184 milled channels. So we kind of used a generic pipe for the upper nozzle and the combustion chamber, and the channels were considered in the heat exchange area. So, we had 2 by 3 millimeter sections that we imposed, 300 watt per meter squared per Kelvin of convective heat exchange into that coefficient. And the heat exchange between the structure and the structure of the engine and the fuel is triggered by the fuel mass flow rate, right? And that's where you want this, that in case of the zero flow, when the engine starts or when it's shut down, we're modeling that heat exchange and how we can go into maybe some excessive fluid flow temperature, right? So we added in this first order lag to really not have any computational issues. But the propellant pressure we set to 17.7 bar A. So when we look at the radiative cooling, we know there's two different cooling methods when we look at rocket engines. And that's really based on simplicity and weight of the design. So due to the large area and lower heat flux of the nozzle extension, our radiative cooling is sufficient to avoid the melting of the nozzle. We use a specific submodel or calculation embedded inside of those components to represent that radiative exchange between the nozzle and the environment. So what you're seeing here, right, again, these radiative components. Okay. The last is kind of the results of this first part of developing this model, right? We developed this ASYS engine and compared it to test data, right? So AIMSIM spits out or gives you a whole bunch of variables or outputs per the component, per the fidelity. But what we're seeing here is the structure temperatures and heat loss and the different fuel temperatures, right? So these are all plotted via function of time. On the left-hand side, we see the combustion wall chambers, the upper nozzle wall chamber, as well as the lower nozzle, and doing the level of comparison there. We know that the nozzle should not exceed 1050 Celsius, in which we compare that to the model itself. But that being said, the structure temperature of the combustion chamber and the upper nozzle are definitely too high. So that indicates that, the structural part should be redefined or redefined or set up into the model itself. We didn't really have any geometric or material information for that regenerative cooling. So we just kind of knew that that was one way to exceed or improve the model with its fidelity. We know that most of the heat loss is dissipated through the regenerative circuit. So when the propellant flow stops, right, it's dissipated through radiation rather than that conduction through the piping. So we know that the boiling temperature of MMH is 360.65 degrees Celsius at 1 bar. So kind of for the fuel, if we looked at altering or making this model higher fidelity, you'll see we add different tanks and we add different flow valves, and that's really allowing us to look at better transient capability. We know that, as you see here, when you are decreasing that flow, your fuel temperature ultimately increases exponentially, right, or sharply. This could burn the nozzle, down the nozzle inside of that regenerative circuit. So we could observe, overshoots possibly in the beginning during that starting phase, but just keep in mind, just the capability and the functionality of AIMSIM allows us to look at these different temperatures, these different pressures or heat losses when designing and knowing the requirements of our data or even of our rocket design. All right, and then the last one we looked at for results was just the engine performance, right? So if you see, all of the dotted lines are your test data from literature, right? Which were almost basically spot on for every location where we were able to do that comparison in propellant mass flow rates and mixture ratios, that combustion chamber pressure, as well as we knew the thrust that was required. AIMSIM allows that extra level of fidelity, right? So that extra combustion chamber temperature, the specific impulse, or even the characteristic velocity. All right. So when we really compare this, there's the lack of maybe data or even the lack of helium in the pressure kind of is what didn't allow the mixture ratio to kind of stay the way it needed to. So really improving and knowing that we have possibly access to more parameter sets or more inputs and data, we know that this was a pretty good agreement with what we can offer from a component standpoint and modeling from just open source literature and having this synchronized. It's very important. We obviously don't want the combustion chamber and the flow to cause any issues of explosion at startup, right? So really knowing the right amount of propellant or the right mixture ratio is really critical when we design that engine performance. The bottom parts here, right? You see your impulse and your characteristic velocity, right? Again, or even in the middle, right? These are the pressures. You see that we have, that's the combustion chamber pressure. We were able to almost match the test data itself. So, you know, according to just the specs and what we had as reference, the ACES engine has a vacuum specific impulse of 324 seconds. As you see, we got it at 318 seconds. So that means, you know, we kind of underestimated a little bit by 1.85%. But again, pretty good note of just open source references, taking that initial understanding of having basic geometries to get it to almost match the test results. Just to conclude, just with this section of the design is, you know, yeah, we were able to get a good match, but you know, maybe we didn't get full transient behavior because we don't have the assembly control valve, right? So we just did basic sources and valves to look at that flow, but we weren't able to capture the true transient behavior of what the whole system would look at, right? So we discretize these different subsystems, and those could be developed by different groups and then ultimately integrated together to make sure they all work in the end. So when we look at that fuel pressure valve assembly, right, it's mainly for, you know, the feed to that ACES combustion chamber. And we know that it wants to have constant and controlled flow rates. The valves are basically identical in terms of architecture, but different kind of in different design parameters, whether that's the spring stiffness, the diameters, the flowing areas, as well as, you know, obviously the propellants being different. So they're both kind of these 2-position, 3-port pneumatic valves. But we also had that, because this is a pressurized fed system, we also have that tanks, which the helium tanks that we have. So once the pressurization is done, the first electronic valve opens, and then the second valve in the fuel metering unit assembly, you know, we use different component design capability to model these as well. But again, you know, the pneumatic valve releases the process, the pressure inside the pneumatic chamber, you know, decreases, and the spring pushes the spool to open the orifice or the internal valves. So it's kind of like a shock absorber. The small diameter of the pneumatic orifices will damp the rebound of the valve to get a smooth opening and avoid oscillation during the spring. All right. So the capacity of the volume of the valve grows. So on the second electronic valve, the pilot, this pilots the helium to the chamber and counterbalances. So if you are to look at this further or want to know the different valves architectures, by all means, I'm more than happy to forward on those questions from a detailed level, parameter sets. This will be released with the future version of AIMSIM, the latest release.
Well, great, thank you. Oh, that's really neat to see that you're building that into the software. That gives users a pretty great intuitive start onto it.
I was just looking at the question there. Oh, I know that we're at 4 o'clock.
Yeah, we're kind of low on time. How many more charts do you have here?
So I do have I have 16 more slides, but I thought that we were slotted from 3 to 4:30.
Oh,
I thought it was a 90-minute time slot.
Second. But, yeah, we'll keep going. Sorry, I think that's my. Oh, I see. That is my mistake. Please continue. I apologize.
Oh, no worries. No worries. No worries. So I do see that there's so curiosity, can it be used for internal combustion engine? Yeah. So we have different. So the combustion map generator tool is more to integrate with our liquid propulsion library, but we do have combustion map generation. We have an internal combustion engine library, IFT engine library, where you can do the mapping as well. So there's a lot of embedded tools inside of AIMSIM that you can use. All right, so that AIM-SIM model, kind of that you would see for those valves itself, and we use component design approach. So you see this purplish color is the pneumatic library, and that's the pressurant gas here, right? So we have a low pressure source or the pressure regulated source. Again, there's that input of test data that we saw, very similar from the previous one. Knowing that we are required to kind of keep a fuel mass flow rate, the goal is to match it by setting up the parameters of the valve. So we did like here's our drag and drop components of our position valves. But then we have the ability to, design the valve itself, right? So we have the seating of the valve, the mass, we can change the diameters, we can change the stiffnesses, the chamber volumes. And this really allowed us to validate and design these valves without knowing the pure geometries to match the test data, right? So this is that component design configuration tool. So this really allows us to look at the orifice dimensions, the spool displacement, so we can put in our different component parameters. We say, hey, what's the displacement of the spool, right? And then we have our rod diameters, the number of orifices. So this is an embedded app inside of AIM-SIM where we can determine that flow area of the orifices when the spool is in steady state condition. So it gives us a better understanding how to parameterize these valves. And we can then also get some different levels of fidelity within the component higher than we would maybe from a drag and drop capability. So we did kind of this analysis based on mechanical end stops. So the pneumatic chamber, we adjust the piston size. It must be large enough to counter the spring force with that high pressure to keep the valve closed. So the variable orifices next to that combustion chamber, we use a check valve to avoid any backflow, which you saw in that previous slide. And we know that because the combustion chamber normally is high, we use the variable orifice to kind of keep the pressure of the MMH to model kind of that burst disc that normally explodes when there's a certain pressurization. So we wanted to really just avoid any flow leak in that design. So back to kind of even the comparison, right? We have that flow rates where we have from our tests, right, our fuel flow rate or even our pressure signal that we got from literature, and you're able to see from basically matching that how it's going to alter our flow rate in our different valves, how it's going to alter the pressure in the different locations, and we can see what the different displacements, flow areas are of those valve itself, right? So we really know that the synchronization of the valve and the detailed modeling really allowed us to improve the agreement between this mass flow rate that was computed to the one that was in the test data. But the main conclusion of all of this, right, is we're building higher and higher fidelity of that subsystem, right? So we could have just dragged and dropped the valve, but having that detailed level approach and having a better capture of that transient behavior allows us to mitigate any issues downstream of our design process. So the major conclusion as well of where you would go from there is, all right, we designed the engine, we designed the pressure control valves, we didn't do the tanks, and we haven't done for the pressure regulators. So yes, we're improving this transient behavior by using this detailed valve assembly. How do we go and keep modifying our simulation model to really mimic what the actual real world example would be? So then we did the propellant tanks. So this is kind of the biggest part when we talked about before of the vehicle mass, right? So the dry weight of this is about 1,200, a little less than 1,300 kilograms. And then when it's fully loaded with all of its propellant tanks, it's about 11 tons. So we had an architecture of 4 tanks, 2 MMH and then 2 nitrogen tetroxide tanks that are, like I said, roughly that 11 tons, right? So 3.2 tons of MMH and then 6.6 tons of the oxidizer. This is what the model would look like inside of AIM-SIM. So again, left-hand side, we have those fluid definitions, our different gas definitions. and we have different attitude and acceleration. This is part of our design process where we can have different external forces on these tanks themselves, looked at different dynamics. And then we have that import of test data. The middle one, right? So the right-hand side, which is the model itself or the screenshot of the model, we set all of the attitudes and acceleration to be 0, but you can alter them. But we see that this helium regulator is split into 2. And starting from the top, we have like a variable pressure source and temperature source, and then downstream we have the 2-stage regulators. These are our latch valves. But then we have the gas flow that goes into different ullage of the 2 tanks. And the gas flow through those latch valves, you see these kind of lumped. They're what we call modular piping system. You can do individual sections like you saw in the first model where we have our bends or our different discretized pipes, or it can be lumped into this one approach, but still takes that discretized level analysis underneath it, and you can get that modular capability. Okay. And then we have different pressure regulators on the bottom, and then mass flow rates representing kind of the fuel and oxidizer consumption. All right. So you had saw in one of the previous examples that we used spheric tanks. So we can take that CAD geometry, similarly of what we did, we did a co-simulation and leverage the solver of SimCenter 3D. We can take our CAD geometry and import that into AIMSIM using what we call as a CAD import tool, and it will take all of the definitions for you, right? So we have CAD import for tanks, where you can slice it and look at different wet surfaces through the different dynamics of acceleration and external forces. And then you can get different bend areas or radiuses. You can have a better understanding of those pressure drops or flow coefficients based on the actual geometry from the CAD. This is where we defined, or how we defined each individual tank, right? We had a specific area, but this can be imported and used and placed as parameters inside of our AIMSIM model, right? So you see those 4 different tanks that are there, and then the round spheres are those helium pressurized models, or those pressure tanks. The next one I had mentioned, kind of modular piping assistant. So you can use CAD import, similar to what you saw before, where if you had the CAD geometry, we chose to do modular piping assistant, where you can pick the number of segments. You can say, okay, this is a straight pipe, this is a bend, and you place the geometries and the parameters on it, and then it will ultimately develop the high fidelity model, including all of those geometric calculations embedded inside of the AIMSIM component. So we looked at the results, right? Again, test versus simulation. We were pretty much, again, almost spot on when we looked at the pressure of the ullage in the 2 tanks. We knew that the orange there is the latching valve fractional position, but that's how we were ultimately able to match our testing data to our simulation data. But then we were able to go one step further from what we got in the literature and said, okay, well, how do we then also look at the tank temperatures of the gas, the liquid, the various heat flux? And that's where AIMSIM provides that added benefit, right? We're dragging and dropping these components and parameterizing them based on whatever we have through that design life cycle, but we might not have all the parameters, and understanding and knowing, real world versus test. And that's where if we could minimize testing and ultimately benchmark a simulation and validate it, now you're not spending billions of dollars, trying to do these launches or really mitigating issues in your propulsion design. So once we get those tanks designed, the next thing, or the last part before integrating everything together, is that 2-stage pressure regulator. So this is regulating that helium tank, and we know that obviously everything downstream is going to have a massive impact. So this is obviously a pressure-fed cycle system. So the parameterization of this regulator is very sensitive, and it's largely going to have an impact on the rest. So the dynamics of the valve depends on obviously the pressure of the propellant tanks and the pressure of the helium tanks. So we kind of wanted to be able to control and mitigate and compose such a stage system to be able to match that, right? So the pressure inside of the helium tank evolves from 400 bar A to a 60 bar A. So a single stage pressure regulator could not have the actual progressive behavior. So we kind of had to do it over the two-stage process. This is what the model or AIM-Sim development would be, right? So on the top part, you have our two tanks that we talked about. We have a filter, different valves, and then our high pressure regulator and our low pressure regulator. And this is obviously the regulated pressure that we need downstream, right? So the volume has a total mass of 34 kilograms of helium, and we have the initial pressure of the tanks to be at 400 bar A. So they're supposed to be ideally insulated due to the lack of information. We really didn't look at heat exchange or materialism involved. But the two stages have the same architecture, and they're modeled using that component design like we saw in the past. And really, they're just made, they have to counter the force of the spring. So the high pressure chamber and the low pressure chamber is where we kind of had to discretize and change the different levels or spring damping or sizing of the chamber or the way the valve dynamics work. Keep in mind, right, this was set using open literature, so the goal was really to match the intermediate pressure. So the intermediate pressure is between the two regulators, and that's where we have that sensor chamber there. Okay. Oh. Sorry. So we were able to pretty much match that test data when we did our design, and we saw that the total helium of the tank went down, and we can look at the mass in the tanks as well, but we were able to match that test data to intermediate, so between the two valves, to get our two stages. So the dynamics extremely similar. The pressure at the end of the thrust phase, obviously we can improve based on that intermediate chamber. We just maybe could have overestimated it or changed some of the parameter sets to have it ideally match it as well. But the great thing here is you can see that even through the decreasing of that helium mass, at the end of the thrust phase, we still have 14 kilograms available. So that's not enough for the passivation stage. So to clean up the system, we could maybe eject the surplus of fuel or maybe design a better propulsion analysis there, or change our parameters of the tanks. Then, okay, we broke down all the subsystems. Now, the last part obviously says, okay, we have 5 different groups or 5 different models. How do we link them together? How do we integrate them together? And those are going to include that engine that we saw, that pressure valve assembly, those tanks, as well as the pressure regulator that all match that test data to ultimately match what you would have as a prototype for this whole EPS system, right? So this is what the AIM-Sim model would be like. You see them all connected together. So you have those 2 pressure tanks, right? The pressure regulator valves like we talked about. Here's our oxidizer and fuel tanks. And then your pressure valve assembly connected up to your engine itself. Again, we have kind of these different components on the side, but we have the test data import, and this is how we were able to really validate the process of confirming that our EPS integrated model would work the same as the different subsystems as a whole. Right. So if you look at kind of that test per simulation, again, we got almost exact same results. So we were able to look at the fuel mass flow rates, which you see on the bottom here for the different combustion chamber, for fuel, for the oxidizer, as well as the mixture ratio. And then we knew the thrust. And again, this was from open literature, from those references. But we were able to still get that specific impulse that we had talked about before, as well as the characteristic velocity. So the crawl, walk, run approach is always the great approach when you really look at analyzing these type of high level or high fidelity system models. So last part on the bottom, sorry, I forgot to mention, we were able to look at the helium temperature as well as the radiative temperature heat flow from the nozzle. So the last thing I would say, and really to conclude, the whole process here, right, as extreme as it might be or as in-depth as it might be, this development really was streamlined because of utilizing one tool that offers a whole bunch of embedded tools underneath that allowed you to parameterize based on testing data or minimal data. But then it has this openness to run different design parameters to size or trade-off studies to really reduce the cost or reduce any integration issues you have downstream later on. But you can have controller logic. Maybe you develop them in Simulink. Maybe you have other teams that are just developing controls, and you can take that controller logic, import it, or co-simulate with a high-fidelity plant model to make sure that physically you're not running into any integration issues. And that's where you take advantage of this collaborative capability, right? We talked about SimCenter 3D linking up with AimSim for thermal system design, right? You're collaborating between those two different teams. You saw on like even the previous demonstration, right? We're collaborating through the different levels of trade-off, right? Maybe someone's designing the gas generator, maybe someone's designing the hybrid architecture or the electrical architecture, and we do that trade-off study, and maybe we have different maths or geometries that need to be altered through that R&D type phases. And then this last one, you might have 5 different groups designing the different subsystems themselves based on expertise, and then collaborating, able to put them together and minimize what you would need for the testing or prototyping in the long run. I did want to keep 5 to 10 minutes here at the end if anyone did have any questions, but I really appreciate everyone for listening to what I had to say today. And this is my contact information. I'm a SimCenter solution consultant with a focus on AimSim. I work a lot in the aerospace and defense industry, and as well as the space industry. So I would love to help anyone through the design process if they have any questions with AimSim or have any integration functionality questions that they had. By all means, here's my contact information. If we need to grab in any domain experts, I'm more than happy to as well.